Hello, welcome to this additional factor analysis practice activity. So this is designed to sort of supplement your learning on the recent teaching block. And we'll be looking at performing a factor analysis and thinking about these sorts of practice questions, getting you to think about which type of rotation you performed and why, whether the data that you have satisfies the assumptions for performing a factor analysis. Looking at the output, so with any statistics, they're a tool to help you with your decision making and your interpretation of the patterns in the data. So we'll be looking at the aspects of factor analysis that can help you decide how many factors may be underlying your data, how many should be extracted, and what the optimal solution from the factor analysis can tell you about the nature of the thing that you are studying. So all of this information is available on the Blackboard page, and as part of this, what we'll be doing as well is having a look at the data set there. So this is the data set you have. So the scenario is that you have some information on a number of individuals. So if we have a look at how much data we've got in here, you can see that we have 459 individuals. We can see that we have both males and females who've participated. We have some information on their age. And if we look at the variable view, what we can see is that these are all indicators of personality. Now, this is based on the five-factor model of personality. So this is the aim of it. And what we're doing is we're imagining we're validating a new measure of that five-factor measure of personality. So what we want to look at is, do we find five factors in the data using factor analysis? Do the items come together in a way that makes sense in relation to that theory, and so on. There's more we could do with that data as well. We could look at how, once we've got an idea of the number of factors in our data set, we could look at how they differ based on gender and age, but we're just going to concentrate on actually that initial step and looking at how these items may or may not group together into different factors. So one of the first things we need to do is to get a sense of what's going on in our data. So what we need to do is to look at Analyze, Descriptive Statistics, and Explore. Now I'm just going to do it for the one variable. You notice here it's been entered as an ordinal variable. So if you want to have a look at the debates, the controversies around treating Likert scale data as ordinal or interval and the impact of that on factor analysis, then I really recommend having a read of the factor analysis chapter in Andy Field's book, where he talks about that in sort of and other issues relating to sample size and all sorts of things on the interpretation of factor analysis. So what ideally we should be doing is looking at how each of our items perform. So I'm just going to look at one for now, because there are obviously quite a lot here. But as part of your practice activity, I'd recommend actually looking at every item. But we'll have a look at the talkative descriptor and the extent to which people agreed to strongly disagreed with that. And we'll look at plots, look at histograms. I'm going to take the stem and leaf off. That's a personal preference. If you prefer that, then keep that on. And I'm going to ask for normality plots for the tests. Options, I'm going to ask for listwise deletion. Now, you'd have to make a decision whether you're going to look at listwise or pairwise, or quite how you're going to handle the missing data. Because just from eyeballing this data set, we can see on personality item number 15, for this individual, person number 12, we definitely have missing data. So there is missing data in this data set, and you'll need to decide how to handle that. For now, I'm just going to treat it as listwise deletion, and click continue. And then I'm going to click OK. Okay, so what we've got here is some information. So we have for this variable, the talkative descriptor, We started with the 449 cases, but actually we have missing data for 10 participants, so we'll have to consider how we use that. In this case, what we've done is we've asked those individuals to simply be dropped from the descriptive statistics and calculating the normality and things. So what we can see is we've got a mean score of 3.6, so that's we need to look at that in relation to actually the maximum and minimum possible scores to get a sense of what that means. So if we look back at the data, let's see what that is now. So we go back to variable view. We can see that people could have scored between 1 to 5. So actually they're hovering between 3 and 4 then, on average. So what we're also looking at is the trimmed mean. So the trimmed mean is a good indication of whether there are any really extreme values on your variable here. So if there's a big jump between the mean and the 5% trimmed mean, so a jump between these two values, then it's quite likely you have an extreme value in your data set. What we can see here is actually a mean of 3.6, and then when we chop off the tails, the really extreme values from our data set, it doesn't have too much of an impact on the mean. So actually it's quite close, 3.67. So that's a good indication that there aren't any really extreme values, but we'd want to do a bit more poking really to know that for sure. So we've got, again, confirmation of the minimum and maximum values that were scored in the data set, not necessarily so that's what's actually been observed, so that's good. We've got a good spread of scores. That would help us identify whether there are any floor or ceiling effects. So if that was kind of a 2 and a 4, then we might have some floor and ceiling effects, but that's good. And what we can see here is we've got skew and kurtosis values. Now, these are within plus or minus 1, so that's usually an indication that it could be okay, that there isn't too much skew, that there isn't too much kurtosis. So skewness is whether the extent to which your data, the variable, is not symmetrical, so it's got a tail. So if it's got a negative value, you've got a tail over the lower end. I mean, I can actually see this in your histogram. So you've got a tail to the lower end of scores with a peak to the right-hand side of the graph. If it was a positive value, you'd see the opposite. So you'd have a long tail over the higher scores on the variable, and then a peak, most people scoring lower on that variable. Now, what our test normality suggests is it is significantly different from a normal distribution. And actually, if we're looking then at our histogram, it would suggest that there is some deviation from normality, and you can see that again in the box and whisker. If it was perfectly normal, this would be in the center, and these two error bars, these two kind of whiskers would be of equal length, and they clearly aren't. So there is something going on with the data in terms of being not normally distributed. So ideally what you need to do is go through and look at every one of those items to see what is going on. Now, why am I doing that? Well, it's an assumption of factor analysis that it's a parametric test. So there's an assumption that actually your data will be normally distributed. Now, if you don't have normally distributed data, it's not too much of a concern, but it will have limitations in terms of not performing the analysis, but of the extent to which you can generalize the findings. So actually, if you look at Andy Field's book on the chapter on factor analysis, he talks about the impact of non-normally distributed data for factor analysis. And what it means is you should really try and constrain your the conclusions you draw, the interpretations to your sample, and not try and generalize beyond your sample, because you may be on shaky ground. But it doesn't mean you can't run a factor analysis per se, it just means you need to be a bit more cautious with your interpretation of the results. So that's why it's important to do that. In practice, I'm not sure that a lot of researchers do, but that's not good practice. But what you would do is you'd do that for every item and get a sense of what's going on with the data. So what I'm going to do now is I'm going to take you through some of the steps in running a factor analysis. Now, I'm assuming, based on previous research about the 5 factors of personality, that there is no good reason to believe that any underlying factors or components of personality would not be related in some way, at least to one other component. There's a lot of research out there that suggests that some of the 5 factors of personality, the 5-factor model, do relate to each other. So when we're running an analysis, a factor analysis, we need to allow that factor analysis through the rotation we choose to allow our factors to relate to each other. And that means that we need to choose an oblique rotation. And the most commonly used form of rotation is the direct oblimin. If we wanted to force our factors of personality to be totally independent of each other, then we would need to choose an orthogonal rotation. And the most commonly used orthogonal rotation is Verimax. Now, there is a huge debate. For example, Andy Field argues that actually there's a big question mark over whether Verimax should ever be used in psychological research, or you should at least do a direct oblimin rotation beforehand to see if your factors do indeed relate to each other or not, before deciding whether or not you can do a Verimax rotation. Why people do a Verimax rotation, or quite often what you see in the literature of the Verimax rotation, is easier. It's easier to interpret, so that's why people do it, but again, that's not best practice. So we're going to do an oblique rotation, and we're going to do a direct oblimin rotation. So we go to Analyze, we go to Dimension Reduction. So this is all in your factor analysis walkthrough. So all of the information I'm going through here is in the walkthrough. You can go back at your own pace through that, and the walkthrough will break it down with a different example data set. So this is an additional activity. So we go to Factor. Now I want to transfer over all of these items from the questionnaire. I don't want these because these aren't actually meant to be part of the questionnaire. They are demographic information and kind of unorganizational variables. So I don't want to copy those over. I only want to look at the relationship between these items because they're supposed to be part of the same questionnaire, measuring specifically 5 factors of personality. So then first thing I need to look at are the descriptive statistics. I'm going to ask for the univariate descriptive statistics to be produced. And that gives you a sense of where people are scoring on each of those items. Now you may have already produced those if you've looked at the distribution of the data for every item, but it's good practice to call it up again. I'm also going to ask for the coefficients for a correlation matrix, and that's because it helps me to check that the data is suitable for running a factor analysis. And another assumption check relating to the suitability of the data that is related to this is the KMO and the Bartlett's test. And we'll look at those in a moment. In terms of extraction, now the default method, we want to do principal components analysis, which is also referred to as which is also referred to as factor analysis. But true factor analysis is actually confusingly principal axis factoring, but we're going to do PCA. We want to just use the default criteria, which is using eigenvalues greater than 1. So for further information on that, look at your walkthrough, look at Andy Field's chapter on factor analysis. But essentially, it's a best guess. It's a best guess at which factors are the most important in the data set. And it's a good place to start. So you should always think of your first factor analysis attempt as sort of a draft, a work in progress. So it's somewhere to start, but it's not necessarily where you'll end. So we also want SPSS to bring up our scree plot. Now that is where we can do the Catel's test, which is a kind of way of double checking the number of factors that we might want to extract. So it provides us some additional information, so we're going to ask for that. I'll click Continue. Now we need to choose the type of rotation to perform. As I said, we want to use an oblique rotation, and the most commonly used of that is the direct oblimin. And I want to ask for the rotated solution to be provided. And the reason we're doing that is it makes it so much easier, and you'll see this in the output, to interpret your factors when you perform a rotation. And you'll see why then we do it. The next thing I can leave everything in the factor scores as blank because I'm not at this point interested in creating factor scores. and look at the options. Now, this is again where you're going to have to decide, similar to, say, regression. How am I going to handle the missing data? So these blank cells, what am I going to do? Now, for brevity and for kind of ease, I'm going to choose to do listwise. But there are definitely pros and cons of doing listwise and pairwise, and you'd need to really look at what those are and make an informed decision based on your particular research context, the number of participants you have, sample size, all those sorts of things. For this example, I'm just going to choose listwise. And then you need to choose sorted by size. That just makes it so much easier to interpret your output. You can suppress all of the small factor loadings, but I don't want to do that. I want to actually see everything. I want to see how everything relates to everything else, so I'm not going to choose that option. And then I'm going to click OK. Okay, so we've got our descriptive statistics, so we can see roughly where the central tendency lies of this data. We can see the spread outness of scores around that. We get a sense of, okay, because I've used listwise, although we know we had a higher number of participants to start with, I think it was 459, we know we've got not a huge amount of missing data, but we've definitely got missing data. So our N for the analysis, using listwise deletion, has resulted in 433 participants. So you need to have a look at things like sample size guidance to decide whether this is appropriate. I would have a look at Julie Pallant's book and Andy Field's book about sample size considerations and factor analysis, because it's actually not as simple as it first sounds. So there are a lot of factors that influence how well how suitable data is for factor analysis. Sample size is one of those. So yes, I'd have a look at Andy Field's book in particular, which will give you a good overview of the issues, the challenges of calculating appropriate sample size. Next we have the correlation matrix, and what we're going to use this for is to see, firstly, are there any variables, any items on the questionnaire that correlate extremely highly with each other. So we're talking 0.8, 0.9. What that suggests is that we could have some redundancy, and actually factor analysis won't work very well if you have items that correlate really, really strongly with each other. You'll notice all the way through there's a diagonal line with a perfect correlation. That's nothing to worry about because it's the item correlated with itself. So just eyeballing this data, we've got some high-ish correlations, some strong correlations, but not very, very strong correlations. So that's a good sign. That's an indicator that we can proceed with the analysis. The other thing we want to check is that each item has at least a moderate correlation with one other item. So if you've got very weak correlation, so say if you've got something looking like this for this item tense with every other item, that would be a cause for concern, and actually probably what would happen is this variable wouldn't load, wouldn't seem to relate to any factor in our factor analysis, and could potentially be dropped to improve the solution. But actually this one does have a moderate correlation with depressed, and so on. So actually what you're looking for is a good spread of moderate correlations. That's what you want to see. So that's again an indicator that the data, there are enough relationships between the items in the data set to be able to analyze it meaningfully using a factor analysis. An additional way of checking that is the KMO and the Bartlett's test. So the KMO, a measure of sampling adequacy, this kind of gives you a value that on the degree to which your items are kind of related to each other. And you need this value here to be 0.6 or above for it to be suitable for factor analysis. So we can see that that is above 0.6, so that's a good indicator. Another thing we can check is the Bartlett's test of sphericity, and we want this to be statistically significant, and it is. So again, these all suggest that the data is suitable in terms of the strength of relationships between the items to perform a factor analysis. The next piece of information we've got is the communalities. So there's some more information in your walkthrough about communalities, but essentially they give you an idea of how much variance each of these items shares with the other items. And what we're looking for here are values that are below 0.3. That would suggest that the item has little in common with all the other items in the questionnaire. What we can see actually is these are pretty high communalities. So actually it would suggest that it's supporting all of these earlier assumption checks, suggesting that there is enough shared variance between the items to perform that factor analysis. So what we're going to look at now is the total variance explained by the factors that have eigenvalues of 1 or greater. So this is based on the Kaiser's criterion, which is where you extract all those factors that have an eigenvalue of 1 or greater, because that's an indication that they could be substantive. They could provide, they could explain a useful amount of variance across the data set. Initially, with factor analysis, you start with as many factors as there are items. So these numbers should not be confused with the item numbers. These are actually factors. Okay, and we're trying to sort the wheat from the chaff here. So what we can see is actually the first 5 factors have eigenvalues greater than 1. That suggests that they explain a sort of larger proportion of the variance in scores just based on these 5 factors than having more and more and more. And what we can see here is that in combination, those 5 factors explain 58% of the variance in our data set. So that's a fair amount that actually by reducing our information down to 5 dimensions, 5 factors, we can explain 58% of the variance in people's scores. So actually that's quite a useful thing to know. But we don't know that that's the best, that's the optimal solution. So what we need to do is check a couple of other pieces of information. And the first one we want to look at is the scree plot. So this is where we can perform the Cattell test. The Cattell's test is where you're looking for the point at which the slope of this changes noticeably. And the idea is that as soon as the line starts to level out, we think of this as a cliff. So this is the most important factor, second most important, and then everything here is like scree falling down a mountain. So everything here is essentially noise, it's rubbish. So we're looking for the point at which that slope changes, and it's a little bit, there could be a couple of little elbow points, which is what we call this elbow point, the change in the slope. The most noticeable one is perhaps here, and it occurs on the 6th eigenvalue. Now the Cattell's test suggests that we would take all factors above that to be useful. So not on and above, but all factors above it to the left. So we can see actually it's suggesting that 5 factors is potentially the optimal solution. And that's what's been extracted actually. So what we could also do to further that, to check it, is perform something called a parallel analysis. And I'm just going to briefly show you that. So in order to run a parallel analysis, we need to know the kind of parameters of our analysis. We need to know how many variables we have, how many participants we have, and then we need to set a number of replications. So usually the typical for setting replications is 100, so we'll leave that at the default kind of 100. In terms of the number of variables, how many we have, well, we can see we've got 23 factors. We know initially there are as many factors as there are items, so we have 23 items measuring different parts of personality. And then we need to know it calls it subjects, but we're talking about participants here, so we know from the beginning that we had 433 participants. So those are the parameters of our analysis, and I'm going to get it to calculate it. So what this is actually doing is running a simulation. So it's looking at random eigenvalues based on 100 simulations of data with 23 variables and 433 subjects. So if there was absolutely nothing going on in the data, what would we expect to find in terms of eigenvalues? So I'll just pop that there. And that next to it. And what we need to do to help us decide whether 5 factors makes the most sense is look at the random eigenvalues and the eigenvalues we've observed. Now, if our eigenvalue is larger than one that would be expected purely by chance, then it's safe to say that there's something going on, that is a substantive factor, that it is doing something meaningful, that it makes sense to keep it. So the first factor or component, as SPSS calls it, the eigenvalue that we have identified is 4.868. So we look at the random eigenvalue where there's nothing going on between the variables. It's definitely higher. So that suggests that definitely the first factor we need to keep. So now we'll look at the second factor. The random eigenvalue is 1.3650, and we can see that the eigenvalue that we've observed is 3.306. So again, that our eigenvalue, the observed eigenvalue, is much larger than the one expected by chance, so it's safe to retain it. So eigenvalue, the third factor is the random eigenvalue is 1.3, and the third, the eigenvalue of our third factor is 2.31, again higher, so we can continue. Next we look at the fourth. We can see that's 1.27. Compare that to ours. And they're starting to become more similar, but again ours is still higher. That suggests that it's safe to retain that fourth factor. But they are starting to converge here. And when we look at the fifth factor, this is throwing out a surprise. So what we've got here is a random, by chance, when nothing's going on, you would expect to find an eigenvalue of 1.22. That's actually larger than ours. So this fifth factor might not be that useful to us. It might be a bit weak, essentially. So what we need to really think about is perhaps rerunning the analysis and looking at 4-factor solution. But at this point, it's really important to remember that these are statistical tools to help you with your decision making. Now we know that we're looking for a 5-factor solution, so we need to look at this on balance and see how does the rest of the output perform. But it would all help us understand how the questionnaire overall performs and where it might need to be developed and improved. So I'll quit that now. So for the moment we'll stick with this 5-factor solution. Now the component matrix, this is the unrotated solution, and you can see what we're really looking for here, and this is all again all in your walkthrough, are the really high factor loadings. And that would suggest that there's a particularly strong relationship between the item and that factor. Now, when you haven't run a rotation, it's very hard to interpret because almost all of these items will load highly, firstly onto the first factor, then onto the second factor, and you'll end up with very few things loading highly onto your fifth factor. And it just basically isn't that user-friendly. So we want to look at the rotated factor analysis results, and with the direct Oblin rotation, these are called the pattern matrix. This is the thing that you want to use to tell you the relationship between each of these items, the unique relationship between the item and the factor. So these are effectively regression coefficients, and what we're looking for are the really strong relationships. So there are different ways, different kind of cutoff levels, but one of the ones that's commonly used was devised by Stevens in 1992, and you can find some information about that in Julie Pallant's SPSS Survival Manual. But we're looking for that criteria, it's 0.4 and above. But it really depends on the context you're looking at. You might want to set that much higher, and some researchers will only consider those items of 0.6, 0.7, 0.8 and above, because that suggests there's a very strong relationship between the item and the factor. And why we're doing that is that when we start to see how the items group together, so this is factor 1, we can see that that's kind of made up of relaxed, emotionally stable, calm in tense situations, tense, worried, depressed, nervous. So we can see, and actually you can see these items have negative factor loadings. So they have a negative relationship overall with the factor, whereas these items have a positive relationship overall with the factor. So what, if we were thinking back to our theory, the 5-factor theory of personality, I would suggest that's neuroticism. Okay, and these represent the characteristics at the one end, the pole of that factor. So you're relaxed, you're calm in tense situations, and these represent the characteristics at the other end of the pole, nervous, tense, worried. So I think these are the characteristics which, based on existing theory, reflect neuroticism. What we need to do next is look across and think, okay, so what's factor 2? How can we describe factor 2? And we're looking at the common thread between the items that have the strongest relationship with that factor. So we can see here that it starts, there's a strong relationship here, reliable, does a thorough job, perseveres, sticks to plans. Oh, we've got a negative correlation here between lazy and the factor, and then it kind of stops. So these items all seem to have something that's in common, and on the one end you've got lazy at the pole, and then at the other end you've got reliable, thorough, persevering. I'd say that's probably relates to conscientiousness. So these items seem to be clustering together around that. That seems to be the common thread. So you need to do that for each of the other factors. And the one which we're probably looking at in particularly is this 5th factor, because we know that it was the weakest one based on our parallel analysis. So we want to look at how the items play out. And actually what we can see is we've got some items, uncooperative, that load highly onto more than one factor, 0.4 or above. That's not a good indicator. We've also got a fewer number of items that are making up that factor, which again makes the factor less stable. So the 5th factor is it's not too bad because we have at least 3 items, and that's a marker of a stable factor, but it's not brilliant. And actually I think if this was looking at the future directions, we need to look at what this 5th factor is supposed to be, and we'd need to perhaps look at amending these items, going back out, doing some further research to see if we can improve that 5th factor. The structure matrix looks at the correlation, so these are correlations. So quite often you'll see they mirror the pattern matrix, but they won't be exactly the same. But when you're trying to identify and name your factors, you should use the pattern matrix. Don't use the structure matrix. And the component correlation matrix is the one that tells us whether our factors are related. Now this is useful for a number of reasons. So if theory says that our factors should be related, which some theory does suggest, then we want to see that in this. This is essentially, these are correlation coefficients between factors 1, which we know is neuroticism, and factor 2, which was conscientiousness. So what we can see is that there is a negative relationship, which would be supportive of research, previous research, but it's actually very weak. So we need to perhaps consider that in relation to, well, what does that suggest about the quality of our questionnaire, or does it suggest something about the theory that is based on that we need to consider further? But also some of these are very weak, they're very weak correlations, so actually we could make an argument about using a varimax, but I think based on theory, where we would expect to see a relationship between the factors, the personality factors, it is safer to use a direct Oblin rotation. And although they're quite weakly correlated in most places, there are some correlations, and I think forcing them to be independent of each other would be misleading. So I would use this to suggest that we do need to do a direct Oblin rotation. So what we're thinking then is using this information to reflect on the quality of the questionnaire and what we might do in the future. So really I think the efforts would need to be around improving that fifth factor, which seems to be less stable, less robust than the others. Hopefully that's been useful. If you do have any questions, please just get in touch. Okay, thank you.